All right, everyone. So here's our first question. What is Y? Temperature. And what is X? Minutes. How hot is my coffee right after I make it? 190 degrees Fahrenheit. Yes, I have measured it. That is true. When I do my coffee, I make it 190 degrees exactly. 0 minutes after I poured it is 190 degrees. Does it get hotter or colder as it sits? It gets colder as it sits. How much does the temperature change per minute? 0.3 degrees. I should turn that off. And last, tell me about an X value you picked, and how did that go? Who picked a reasonable X value where you ended up with a reasonable answer for Y? Sure, go ahead.
I put 3 minutes, and I got my temperature for my coffee at 189.1.
3 minutes. So we have our temperature. So at 0 minutes, we're going to cross the y-axis at 190 degrees. And you said after 3 minutes, which is not very long, you got 189?
Mm-hmm. 0.1.
190. This is minus 3. 3 minutes later. Okay, who else has a value? Yeah.
I did 5 minutes.
Okay, how cold are we at 5 minutes?
188.5.
At 5 minutes, we're at 188, still right around here. Someone here had 6 minutes, 188. Anybody else? Yeah. 10 minutes? 187. We've got this really nice, very clear line. Why are all the points on the line so far? Yes, because they're the predicted values, not the observed values, the predicted values. Anybody pick a very large number? What if it's at for 200 minutes? What's our expected score if it sits for 200 minutes? 120? I actually don't know. I haven't done the math. I'll get my calculator. At what point does it start to get unreasonable? 130 degrees, is that the answer, Colby, for 200 minutes? Awesome. So now it's been 200 minutes. I'm down at 130 degrees. What about 900 minutes? What about 1,000 minutes? Because I can do that math. What if I let my coffee sit for 1,000 minutes? How cold does it think it's going to be? I think so. 1,000 minutes times 1,000 times 0.3. Yeah, I think negative 110 degrees. Colby, you're much faster with a calculator than I am. He's got it on the chat. So if this is positive temperatures, eventually this predicted line is going to predict that we are here at negative 110 degrees after 1,000 minutes. Does that make sense? No. Why not? It doesn't really make sense because it's not going to get that cold if I let it sit. We know that from experience. So what does that tell you about what this equation really represents here?
There's a ceiling or a parameter for which is applicable.
Uh-huh. And all of my observations are based on the observations that I have made that have led me to come up with this equation must have all been somewhere the range where that function makes sense. And not outside of that range where that function does not make sense. So what's an example? Susan says, it's the magical regression into iced coffee. If you just wait long enough, it becomes iced. It's not true, it becomes gross. So if we're here, let's think about, for a minute, just the situation like within the realm of possibilities of where this makes sense. So within, say, an hour of pouring this coffee out. What are some different characteristics that might might make your observed score be different than your expected score? The temperature of the room. That's a good one. That might cause some, if it's really hot in here, it might get cold slower. If it's really cold, it might get cold faster. What about something else? Say it again. Amount of coffee. Yeah, that's good. How much is in the cup? A very full cup is going to get cold slower than a very hot cup. Wait, dang it, a very full cup. Wait, what did I say? Everything wrong. An empty cup. That's why that last sip of coffee or tea is always so cold and gross. Colby says material of the cup. What the cup is made out of might help. If you've got one of those fancy stainless steel Yeti containers, your coffee will stay hot longer. So cup material. So all of these things might change how far your observation is from your actual predicted line. And this distance here is a lot of what we're talking about today. What makes an observation not be on the line, how far they are from the line, and quantifying that amount is what we're going to do today. All right, so let's get into that. Thank you for thinking through coffee with me. I wish I could have that not on the screen. Ha! Ask and it shall be given unto you. All right, here we go. Remember what our rules of regression are. I'm just going to remind you before we move on. We have, the goal is to get a predicted y-score for each person. This is the same for GLM or regression. To get a predicted y-score for each person, and each y should be as close as possible to the actual score. That means, when I say as close as possible to the actual score, it means I want the distance between where I observe a person and where they actually are to be very small. Here's another rule. Another rule is that the average error between the predicted scores and the actual scores should equal 0. That just means I don't want to constantly be always guessing that my coffee is 190 degrees, because I know that's going to be wrong. I'm always going to be overestimating how hot it is. I also don't want to be constantly underestimating how hot it is. I want to be right in the middle. And the last one here is the squared difference between an actual score and a predicted score should be as small as possible. Why a squared difference? I'll show you. I'll show you in a second. I won't show you yet. So it tells whether a model is predicting well by comparing two models. That's what these types of models do. You have a restricted model, which is also called an empty model. And think about it restricted as in like, there's like a bouncer at the door saying you can't come in, no predictors allowed. It's restricted access. It's a model with no predictors in it. If you have a model with no predictors in it, you just like know one thing about everybody in your sample, then your best guess of how another person will do on that thing is to guess the mean of everybody you already know. So the mean of y is used as the expected score in your restricted or empty model. Then you're going to compare that, the amount of error in that model, you're going to compare that to a full model. A full model is the bouncer has pulled the thing off the side and lets everybody in. Now you've got predictors in the model. It's a regression equation used to compute the expected score for each person based on one or several predictors. So I already said this, but I'm going to say it again because it's on here. We have 100 people, and you know how tall all of them are. And I have no other predictors. I know nothing else about the people in this room or how tall these people are, other than how tall they are. If I want to guess how tall a random person is, and I don't want to be consistently overestimating or underestimating, I would pick the mean. That's my best guess at how good someone is, how tall someone is. Remember the central limit theorem? Remember the distribution of, frequency distributions look like. The values in the middle occur much more often than the values in the tails. So if an average person is 5 foot 2 inches tall, my best guess when I meet a new person, if I know nothing about them, is to guess that they're 5 foot 2 inches tall. I'm going to be right more often than if I guess a tail. So if I'm going to take that idea into our publications example from last week, which is how many publications does a person have how many years after graduating? And so if the only information I have is how many publications a scientist has, and I don't know how long they've been out of school, I only know how many publications they have. My best guess of a new person, my best guess at Y, is how many publications is the mean scientist has. So my average for Y. And then to figure out if the model fits, we're going to calculate how much error is in that model. I'll show you how that works. It actually works sort of conceptually. It makes a lot of sense, I think. So let's walk through it. Here's my observed scores. I have 15 people, and I have 15 different numbers of publications here. First person has 2 publications, the second person has 4, and so on. The mean of publications is 7.6. So what I've done next is just put the mean here for everybody's use. It's in everybody's cell because it's the mean for everybody. And now I'm going to calculate the difference between my observed score and my expected score. My observed score is still the number of publications each person has. My expected score in this case is the mean of Y, which means in the first one, I've not done a very good job. I'm off by 5. Later on, I've also not done a good job. I've underestimated some people, and I've overestimated some people. So you take the observed, you subtract the expected. This is also sometimes called a residual value. You may see it called residuals in your books. And then we're going to square it. Why would I square that? All I'm doing is making there be more error. Yes. We're going to square it in part to get rid of the negatives. That's exactly right. Makes the math work out better. It's like an absolute value almost of the difference, but it's a little bit different. And the properties of the squaring makes the math work out better in the long run. So once I've done that, I'm going to add together, the squared errors. Remember I squared all of those error terms? So now I've got a sum of squared errors, which they shorten to an SSE. And you're going to see sums of squared errors in every regression and every ANOVA and every GLM you look at. They're in everything. All right, so we have sums of squared errors now. This, and the squared errors also have not just a mean, they have a variance. They have a sum and they have a variance. That's what I have here in my last two values. So let's get a visual of what this looks like if I'm guessing the mean for everyone. So here what I have is a sort of fake graph where I've plotted every individual scientist as a blue dot. My y-axis here is publications, the number of publications they have. That's the only value I have. And then I have the mean, 7.6. And you see that there are some people that are below that mean, and there are some people that are above that mean, because that's how means work. Now, this is not very useful to illustrate the concept, so what I'm going to do now, even though this is not in the model, I know in a minute I'm going to predict this based on number of years of experience. So I'm going to go ahead and plot everybody based on years of experience, even though that's not in my model right now. So I'm going to take those points, and I've just spread them out across this graph. So these are the same people, 1, 2. So here you can see a little bit easier just how far this person is from the observed score from the expected score. Here's my mean of all publications. That's my expected score. The red lines here represent residuals or errors. So this error here is 13.4. This one's a little bit smaller. All right, this is my restricted model. No predictors in it, just the mean. And so, the average squared distance that these points are from the line is the error variance in my model. You could see that this is not a very good prediction. Lots of very big distances away from this line. Does not fit the model very well. So, the model does not fit the data very well, excuse me. So now, we're going to add in a predictor. Once we've added in a predictor, we'll call that a full model because now there's stuff in it, predicting it. And the goal of adding in predictors is to reduce the error in the model. All right, so here's our regression equation. We use this to come up with our predicted scores for everybody, to derive the line of best fit through this points. Last week, we derived this equation to represent the relationship between years of experience, years from PhD, and number of publications. So this right here is our full model. And now we can plot this, or not plot it. We'll do the math to see how much error is in this model now. Here's still our data. This data has not changed. We have the number of publications here on the left, and then time is number of years from PhD. So what I'm going to do is I'm going to use this regression equation the way that it's been designed to plug in my values of x to get my predicted y. So my observed x value here is 1. So I'm going to plug in this equation, 3.11 plus 0.47 times 1, and get an expected y score for this person. And when I do that, I get 3.58. And then I'm going to do it again for the next person. This time I'm going to plug in a 2. My y equals 4. Then what about ID 3? What would I plug in? Right, you plug in a 5. How about 4? You plug in a 7, exactly. And so on, and so forth. Once you've solved for y, that becomes its own value. That's our predicted score. Our predicted y. So now I'm going to take, just like we did before, the observed value and subtract the expected value, and I get a residual. And once again, we're going to square the difference. Look at this. Ooh. And then when I sum the squares, I get 197. You can trust me that I did that. But what do you notice here about these residual values? Anything stand out? There's no wrong answer here. I'm just curious what you see. I already said, ooh, and did this. Why did I do that? Okay, if I have a residual value of 0, where is my point?
On the line.
Yeah, it's going to be right on the line. I did a really good job of predicting that person. I got them exactly right. But did I do a good job of predicting everybody? No. You still see some really big values down here. I've got a 64, a 34. These are pretty big. So now let's take a look at this scatter plot. So here is the new plot with the new line in it based on time and with our predictor in it, our full model. So once again, I have the mean of all publications right here. This is the new regression line we just calculated with the slope in it. The red lines are still residuals. Do you see that they look a little bit smaller than they did before? So before, well, actually, I have a whole diagram. Let's talk about this variance. So I'm going to come back to that. I'm just going to show you all the pieces of this model. So this is a regular old residual from my observed point from my expected line. Now this is the mean of y, which is my restricted model, where the mean of y is used to predict everybody. This right here, the difference between that much of the residual there, that yellow part, is variation in the model that I've explained by including a predictor in it. And this part right here, the rest of this, the blue part, is what's still left over. There's still error in my model. I haven't gotten everybody. No line is going to perfectly fit through this entire scatter plot of points. But what I have done is I have reduced the error by this yellow amount by adding my additional predictor. And so now we have the amount of error in our full model and the amount of error in our restricted model, and we're going to compare them to determine whether one has less. How will we do that? Oh, I'm so glad you asked. We're going to compare the sums of squared errors. One of them has 369, and one of them has 197. So is it less error? By eyeball, yeah, it looks like less error. But is it significantly less error? Is it statistically significantly enough less error that we want to keep it? To answer that, we need to consider something called degrees of freedom. What's degrees of freedom? It's basically the sample size. It's the sample size minus anything that you're using. All of the coefficients that you're estimating get subtracted. But otherwise, it's the sample size. So in my restricted model, my predicted y is equal to the mean of y, which means I'm only estimating one thing, the mean of y. In my full model, I have both a slope and an intercept. So I have two parameters to estimate, a b0 and a b1. And so, in our publications example, we have 15 people. In my restricted model, I have one parameter I'm estimating. So the degrees of freedom for the restricted model are always going to be equal to n minus 1. because I'm only estimating one parameter. So the degrees of freedom for our example is 14, 15 minus 1. Now in my full model, if I only have one predictor in my full model, it will always be n minus 2 because I have a slope and an intercept. Those are the only two things I'm using in this model. If I add more and more stuff, then my degrees of freedom get smaller and smaller. So the degrees of freedom for my full model here is 15 minus 2, which equals 13. And so now to determine whether that significantly has reduced our variance, we're going to put those together into some proportions. So what I have here is my F-test. An F-test is one of those tables in the back of your stats books. So my F-test I have in the numerator the sums of squared errors for the restricted model and the full model. And in the denominator of the numerator, I have the degrees of freedom for those two models. This whole part of the equation, this is all the numerator, is the reduction in error that you have achieved by adding the predictors. It's that yellow proportion of variance based on these degrees of freedom. And we are looking at this proportion as a function of this proportion. This is the error in the full model. So basically you're saying, if I had 500 error in my model, what percentage of that 500 have I reduced? And then I'm going to look that up in a table, in my F table, using the degrees of freedom from those two tests. Well, the difference between these two tests. So in our case, do I have that in here? Yeah, I have it. In our case, all I did was plug the numbers in. In our case, remember our degrees of freedom here is 14 and 13 for our restricted and full models. So here, I don't actually have this here. The degrees of freedom in the restricted model was 14. The degrees of freedom in the full model was 13. And so this notation is telling me that these two things are equal to that. So 1. My degree of freedom is 1 for the F-test. It's the difference between my two models. And so here, I follow these calculations through and I get to 11.386. My degrees of freedom are 1. When I look that up, what I end up with is a significant F-test. So that's how we know that, yes, we have decreased our error in the model significantly. Adding this predictor to the model has done a good job, a statistically significant job of reducing the amount of error here. We're explaining it better. And so now, just to show you that I'm not making things up, here's an output file that has these numbers in it. I'm going to show you how they align. Just bookmark this page because you're going to have to come back to it. Because obnoxiously, they're called something slightly different in every different place that you look. So here, the sums of squared errors from the full model is called the residual, because that's what's still left. That's this piece, the blue part of our equation from earlier, the blue part of that diagram from earlier. This here, the total, is the sums of squared errors from the restricted model. The restricted model, remember, is the one with no predictors in it. We barred them from coming in. It's always going to be the biggest because there's nothing in the model, so it's the worst one. So I've only talked about full and restricted. What the heck is left? right here, this is the F-test. This is the difference between the full and restricted models. And if you can't remember which one's which, you should be able to calculate that if you subtract one of these from the other, you end up with this one. Which means our interpretation here is that we have significantly reduced the amount of error in our model by including years from PhD as a predictor of publications. So, well, I already did this. There they all are again. Here's another one. How much have we restricted it by? This is just hammering in the same ideas. I have the restricted model error in red, I have the full model error in yellow, and I have the regression error or the difference in blue. So the F test is for how much change happened, and was that change significantly different from zero? If you want to think about how this looks, you could think about this idea as variance accounted for. You may have heard that. If I have no predictors in the model and then I add a predictor to the model, I have accounted for some variance. So variance accounted for conceptually is sometimes shown like a Venn diagram. It's the overlap between X and Y. Oh, my transition here was that the errors don't just have a mean or a sum. They also have a variance. So when you do a good job at guessing people's Y values, your errors are going to get smaller in size. We've talked about that a lot. I've shown you lots of diagrams of how things get smaller in size. But they also get more similar to one another. And if you want to look at how much more similar they get to one another, you can measure that with the R squared in our variance accounted for. So we're looking at the reduction in error variance from the restricted to the full model as a proportion of the total variance in the restricted model. And basically, it just looks like this. I have variance in my restricted model, I have variance in my full model, and I'm going to look at that as a proportion of the variance in my restricted model, which is the bigger one. And that's an R squared. How variable are these? How much more similar is everybody to one another now? So I've got our variances from our previous example. And if I plug those numbers in and run it through a calculator, I get out 0.467. And you'll see that show up right here, 0.467. The proportion of variance in Y that's explained by X. Ooh, I'm just not even gonna, So all I'm trying to say here is that if you have a whole thing and you take part of the thing away, the rest of it is still left. So if you've explained this much of it, you haven't explained the rest of it. So that's what this means. What you have not explained is 0.53. If I've explained 0.47. So putting it all together here to interpret these tables, you'll have similar ones in every different type of analysis that you do. Because remember, GLM and regression and ANOVA, they're all one thing. This is telling me that I have a significantly better fit predicting the number of publications when time is in the model than when time is not in the model. And this tells me that 47% of the variance in my number of publications a person has is explained by the amount of time from PhD. And then this part is the review of last week, where once again you can see that we have an intercept and a slope. So this is just reminding you how to interpret those. That an average person has about 3 publications when years from PhD is 0. And for every additional year out of grad school, the mean number of publications increases by 0.5-ish. Okay. How's that feeling? Do you want to do one more? Nobody wants to tell me. If you don't tell me, I'm going to do one more. Okay. Here I have what? Amount of time spent studying, predicting GPA, GRA, predicting GPA. Who can find the outcome? GPA. What's the predictor? Time spent studying. Exactly. So, if you know my outcome and you know my predictor, do you know which of these predictors is going to be in my full model? Time spent studying, exactly. What's going to be in my restricted model? Yeah, nothing at all. Just GPA as my outcome. The mean of GPA. So the first thing we want to do is understand these variables. Then we'll run the model. Then we'll do these interpretations. To understand the variables, I've run some descriptive statistics. You see I have 24 people. I have a mean of 11 on study time. I have a mean of GPA of 2.5. And then if I run a regression, which you'll do not with me, you'll do this with Susan tomorrow. If you run the regression, the first thing you'll get is an R squared. I think you did this last week. Did you run a regression and run an ANOVA last week? On Tuesday? If you didn't, then you'll do that this week. All right. So I have an R squared of 0.734. Remember that is what that means? It's about how much the variances overlap. So we're explaining 73% of the variance in GPA by including the amount of time studying. Next, I'm moving on to this ANOVA table, which has got my F-test in it for the whole model. And you see these guys. Do you remember which one's the full model? The total is the restricted model. I do that every time. This is why I'm trying this new bouncer imagery. I feel like that will help. Restricted is the biggest because we're doing the worst job because nobody's in there. So this one's restricted. Which one of them is now full? Now you got 2 options. Residual. Residual is the full model because it's what's left. Residual, we're talking about the little bits left. And the regression line is the difference between full and restricted. Just eyeballing these sums of squared errors, you see that it was 21, and now it's 5. It's gone down a lot. Has it gone down significantly? Yes. 60, which is statistically significant. Oh, remember how I showed you the math about the degrees of freedom in the F-test? How it's one minus the other? Look here. I'm trying to stay by the mic. Here's 22 and 23. There's 22 in the residual. There's 23 in the restricted model. The difference between them is 1. Woo. Okay, to pull the regression equation for this model, I have done it right here. Negative 0.144 is my intercept, and I'm going to predict that from study time, which is 0.228 times x. What's that telling me? When x is 0, if I haven't done any studying at all, what's my expected GPA? Negative 0.144. How is that possible? It's possible because most likely in this data set, we didn't observe anybody who had 0 hours spent studying. Well, we didn't observe anybody who told us they had 0 hours spent studying, probably. And so now, for every hour they spend studying, their GPA goes up by 0.228. Yup. Here I am interpreting it and interpreting the t-test and the significance test. There's my B weight for study time. Here I did have a significantly predictive relationship, but if I had not, I would just say study time is not related to GPA. You might want to bookmark these too, because you'll need them this week as you do your homework. And if I wanted to do this and say, what's the expected GPA for someone who spends 10 hours per week? You could do that. And that might be useful for you as you're thinking about how to describe the results of your analyses. It would be 10 times 2.28 plus or minus 0.144, I think. Yes? Yes. All right, great. All right, so we did the whole thing. But I walked you through the whole thing twice. So now it's time to do it just yourself. I'm going to show you one. You try it out, and then we're going to do the same strategy we did before. So here I have a new data set that most of you here have not seen before. This is a data set that is, each row is a different make or model of a car. It's not individual cars, it's types of cars. So I have a Honda Passport and a Honda Odyssey and a Hyundai Sonata. And so what this data set has done is they've gotten data about all of the Honda Passports that were sold. How many of them were there? And that's what's on each row. So my inferences are about types of cars and trucks. So I have this data set. It's called car sales. It comes with SPSS, so you have access to it at all times. The basic question I'm going to ask here is fuel efficiency in miles per gallon dependent on whether a vehicle is classified as a car or a truck? And that variable is called type. So I ran a regression, or an ANOVA, it doesn't matter, with miles per gallon as the outcome, or dependent variable, and with type as the independent variable, or the predictor. The variable type is truck or not a truck. So truck is 1 and car is 0. So I'm going to set a timer again. I'm going to do 4 minutes. Get as far through these questions as you can in 4 minutes, and then we'll discuss your answers. Here's our outcomes, our tables that we've been through. This is the R-squared table, the one with the F-test, and our coefficients. Okay, timer has started. Okay, our 1 minute is up. Our 1 minute, our little bit of time is up. Let's see how far we got. How did you feel about number 1? Where do you look for the information about oh my gosh. Where do you look for information to answer question 1? The R squared. Excellent. What did you get for that one? 33%. Yes. This is why sometimes I do the quizzes online and sometimes I do them in person. I like you to be able to talk, but also I like to be able to see what you know. So I try to split the difference. Okay, sorry. Let's do next. Does the full model fit better than the restricted model? Where would I get that information? Yeah, that ANOVA table, where I find the sums of squared errors. Oh, hello everyone. Where I get the sums of squared errors, they're right here. Okay, and so does it fit better? Yes. You know from the sums of squared errors and from what else? That, yeah, significance test over there, the F test. All those significance tests. Okay, next. How did interpreting the intercept in a sentence go? Did you feel good about that? Folks at home, you can chime in as well. I'll take a sacrificial sentence from someone, or I'll call on someone.
So we at home went with to interpret the intercept, just saying that cars get an average fuel efficiency of 25 miles per gallon, with the significance of P is less than 0.001.
Yes. How did you know it was cars?
Because cars are coded as 0, and so the value for trucks will be the constant plus the slope.
Yeah, so the constant is the value when vehicle type is 0. The expected miles per gallon when vehicle type is 0. So that sentence I liked a lot. Did anybody have a slightly different sentence? It's okay if you did. No? 25 miles per gallon is the expected miles per gallon for cars in this model. All right, so then the last question, which has generated a lot of heated discussion in previous classes, so I'm curious how this one went. Who is more efficient, cars or trucks? How do you know?
Because the fuel efficiency goes down by 5.6 miles per gallon.
Yes. Could you hear that at home? I can say it, I can repeat it.
I could not hear that.
Okay, so what they said is that the cars are more fuel efficient, and we know because as vehicle type goes up from car to truck, it increases by 1. The fuel efficiency goes down by 5. So cars are more fuel efficient than trucks. Are they significantly more fuel efficient? Yes. Yes, they are. Okay. Good? All right, let's do a break time. Let's do a 7-minute break today. And then when we come back, we're going to add more predictors.